Hey there everybody, welcome to another Chem Complete episode, and for today's episode we are going to take a look at chemical equilibrium and how to determine equilibrium constants. Okay, so let's get right into it. When we talk about equilibrium from a chemical perspective, we are saying that we can write out a reaction where A can go to B, but instead of a one-directional arrow, like we would see here, we're going to say that it can go both ways. So this is technically a reaction that can go in the forwards and the backwards direction. So there's reversibility that is present here. And we represent that with a single-headed arrow that's going in each direction instead of the double-headed arrow. So that's how it's actually represented there. Now, what does equilibrium actually mean from a perspective of defining it? So there's two important factors here. The first is that the rates of the forward and reverse reactions are going to need to be equal to one another. All right, and then the other thing that we need to keep in mind is that the concentrations for the reactants and products are no longer going to change with respect to time. They're going to stay constant, and that's why we're going to refer to the equilibrium constant. Okay, so one of the things that is important to keep in mind here is that we are not only talking about chemical equilibrium, but we can also talk about physical equilibrium. So for example, if I have water in a liquid state, I can put that into equilibrium with water in a gas state. So this is the equilibrium as the water is shifting back and forth between the two physical states, liquid and gas. And you could do this as well as for solid and liquid, and so on and so forth for any type of physical state change or physical shift like that. You can create an equilibrium. Right? Now, we obviously also have chemical equilibrium, and that's the main focus of the chapter that we're working with here. So for chemical equilibrium, we could consider a reaction such as, let's say, N2O4 as a gas in equilibrium with the breakdown into 2 of the nitrogen dioxide gas. Okay, so one of the things that we mentioned is that the concentration of the reactants and the products are not going to change with time, or they're going to be constant. And so if you go back and you look at the title, it's equilibrium constants, because one of the first things that we introduce to students when you're learning about equilibrium is the equilibrium constant. It's a very useful piece of information in determining reactions and where they stand in terms of are they favoring products or reactants in the equilibrium shift. So when we get ready to define the equilibrium constant, we use the large letter K, and K is going to be equal to products, and it's specifically the concentration of products, okay, over the concentration of any reactants. Now it's a little more complex than this because these can be raised to different values. We'll call it X and Y right here. So these X and Y values are going to come from the stoichiometric coefficients that we have here. So for instance, the equilibrium constant for the reaction with N2O4 would be written as such. You take the products, which is going to be NO2, you would raise it to the stoichiometric coefficient, which is 2, so this would be squared. And then at the bottom, you would have N2O4, and that would not be raised to anything other than just an implied 1, because that's what the stoichiometric coefficient is here. It's an implied 1. All right, so to outline that a little bit further, let's just consider a very generic example where we say A plus B will be in equilibrium with the products C plus D. Now you'll notice that I have a lowercase and an uppercase here. So the lowercase will represent the stoichiometric coefficients, meaning the balanced equation, and A, B, C, and D. The uppercase will represent the actual materials, the reactants and the products. So here I can define the equilibrium constant as the concentration of C raised to the C power times the concentration of D raised to the D power over the concentration of A raised to the A power and the concentration of B raised to the B power. All right. Now, a lot of times you're going to see the K value has a C down here. All right. So the C represents concentration because we can deal with Kc for concentration. You can also do this in partial pressures instead of concentration. So there's such a thing as Kp, and we'll take a look at how Kc and Kp relate to one another in a future lecture. And then there are also things known as such as Ka, Kb, Ksp. All right, and what these are, Ka is the equilibrium constant for an acid, Kb is the equilibrium constant for a base, and Ksp is really what's called the solubility product. It deals with whether precipitates form when you mix ions together, and they can potentially crash out a solution and form these supersaturated precipitate solutions. Okay, so there are lots of different ways. Anytime you're in an equilibrium, you can create an equilibrium constant. So when you see all these different letters that are attached to the equilibrium constant, it's just referring sort of to the mode or the way in which the equilibrium constant is being viewed at that point. And it can be very specific depending on what reactants and products are present there. So just keep all of that in mind. Now, there is something else that's very important that we want to consider here, and that is that the values that are coming into the equilibrium constant are really nothing more than a ratio of the products to the reactants, right? So we can just view this, again, as products to reactants. It's a general ratio. Now, what that means is that if we find a Kc that is greater than 1, that tells us something. If we have a Kc that has a value that's less than 1, that tells us something. And then finally, you could also have a Kc that's exactly equal to 1. That's probably the rarest case, but that would also tell us something. So think for a second if you can realize what these values would represent as far as Kc and its relationship to 1. So Kc that's greater than 1 means that the numerator has to be larger than the denominator here, right? So if the numerator is larger, that's where the products hang out. So a Kc that is larger than 1 means that there is going to be some level of favoring products. Now, when that's said, it's obviously relative because as you continue to get a larger and larger Kc and it rises further and further above 1, then you are drastically favoring the products compared to just a little bit if it was just slightly over 1. And the same thing is true in the reverse. For Kc less than 1, we are now going to favor the products, and that's because the denominator would now be getting larger. Reactants. Did I just say products? It should favor the reactants. I'm not sure what I just said a second ago there. Okay, but a Kc less than 1 is going to favor the reactants. The reactants. So this denominator is getting larger because the concentration of the reactants are getting larger here. And then Kc equal to 1 means we don't really favor either. So there's not going to be any favored position in the equilibrium. We don't particularly have a large concentration of products or reactants. They would be equal to one another, and there wouldn't be favor in one direction or another as far as that. All right, so that is just a useful way of looking at Kc and its value and seeing, okay, at equilibrium, do I favor the products or the reactants in this forward-backwards relationship? Which one is going to be favored in that case? All right, so let's take a look at some examples then and get ready to wrap this up, and then we can get right into the next lecture after this. So what we would like to do now is take a look at some examples. So let's take methanol, and methanol is going to be in equilibrium with carbon monoxide gas plus 2 moles of molecular hydrogen gas. So take a minute and see if you can determine the equilibrium constant. Now again, we're not actually writing numbers in here yet. We'll be doing that in the next lecture. Right now, your goal is simply to define the equilibrium constant as these bundles of reactant to product ratios as far as the concentrations, putting them in brackets. So go ahead and try this one, and then we'll do one that's slightly more difficult right after that. All right, so hopefully you paused the video and you had a chance to try to work through this. So it would be the products and the H2. The key here is that you want to square that because of the coefficient value there, and that would go over the concentration of methanol. Okay, so that would be the correct way to express the equilibrium constant for the reaction shown above there. All right, so let's just do one more to make sure everybody has the hang of it. So this one will be slightly more complicated. We're going to take propane, which is written as C3H8. That's a gas. And we will use 5 molecular oxygen as a gas. Put that into equilibrium with carbon dioxide, and we're going to have 3 stoichiometric moles of that, plus some water vapor, and we will have 4. Right there. So again, pause the video and try this. You should hopefully be able to get the hang of it. Determine the equilibrium constant and express it in terms of reactants and products. So pause the video, try that, and then unpause it when you're ready. All right, so the way that we would do this one is CO2, that's going to be to the 3rd, okay, and then the H2O is going to be to the 4th, and we'd have the reactants, which is the propane and the oxygen. And that would be raised to the 5th. All right, so this is how you represent equilibrium constants as far as expressing them in concentrations of reactants and products. And it's products over reactants raised to the stoichiometric coefficients. That's the key here. Okay, and remember, whenever we start plugging values into this, because we're going to be doing that in the next lecture, when we start plugging values into this, the value of K is going to tell us something. So that means if it's above 1, we're favoring products because that numerator is larger. If it's less than 1, we're favoring reactants because the denominator is larger. And then if you ever come across where they're equal, then we're not particularly favoring one side or another. So that is going to do it for this lecture. Please remember to smash the like button so you can help boost our Chem Complete material in the YouTube algorithm, and I will be able to make more content to help you with your classes. Thank you so much for learning with us, everybody. Remember to subscribe for the latest updates. I am Professor Tomney, and I will see everybody for the next lecture.